So usually with improper integrals, there's a couple that we start off with. I think he did them both in class yesterday. So I'll run through them really quickly because it kind of feels like you have to talk about them. Though, just like I'll change them up just slightly. Let's say we want to look at the integral from 2 to infinity of 1 over x squared. So what we're going to do, and this is true, so I should actually back up. What makes an integral improper in the first place? What makes an integral improper is either type 1, where you have either infinity or negative infinity or both as one of your limits of integration, right? Infinity is not a real number. So that's one way an integral can be improper. The other way, a definite integral, right? Because these are all going to be definite integrals. Another way definite integral can be improper is if the function you're integrating is undefined somewhere on the interval. So that's not this case. This one is just an infinity here. Here's what we're going to do. We're going to look at the area under this curve, 1 over x squared. Instead of going from 2 to infinity, we're going to go from 2 to somewhere. Usually we say b. You can use any letter you want, really, but b is a typical choice for an upper limit. You can just set that down. And a is a typical choice for a lower limit. So we're going to say, great, I want to find the area under the curve from 2 to b instead of from 2 to infinity. Cool, that's totally doable. The integral from 2 to b of 1 over x squared dx is going to equal, well, I know how to integrate 1 over x squared. That's just x to the negative second, whose integral is x to the negative first over negative 1, or negative 1 over x from 2 to b. We're just going to plug in our real numbers here. We're going to get negative 1 over b minus, that's a b, sorry, minus negative 1 over 2. Or written slightly more nicely, 1/2 minus 1 over b. So that's the area under this curve. And you can pick any value of b and get a numerical opposite. Like, for example, if b was equal to 100, then the area under the curve from 2 to 100 would be 1/2 minus 1/100th. And you can probably also see that as you let b get larger and larger and larger, this amount that we're subtracting is going to get closer and closer to 0. So the way we actually deal with an improper integral, say, great, this is going to equal the limit as b approaches infinity of the integral from 2 to b of 1 over x squared. We're going to do the integration and plug in limits of integration. We already did that work, so I don't think we need to repeat it. Just say, great, that's equal to the limit as b goes to infinity of 1/2 minus 1 over b. And then we take the limit and we get 1/2 minus 0, which is 1/2. If the limit exists, meaning it's real and finite, we say that the integral converges, and it converges to that limit value. So that we would say that really we would say, back up. Writing this is enough. You really don't have to say anything else. Because when you say that the integral, the improper integral, is equal to a number, saying it's equal to that number implies all the things I just said. It implies that we know the limit exists, we know the integral converges, and it converges to that value. But if you wanted to be extra wordy about it, we could say, yeah, the integral from 2 to infinity of 1 over x squared dx converges, and it converges to a value of 1/2. On the other hand, not every integral is going to be convergent. And again, I should back up a little bit. What we're saying is, as you go further right, the area under the curve is just getting closer and closer and closer to 1/2. Just like how limits usually work, right? We're getting closer and closer to whatever limit value you have. But some integrals don't converge. For example, the integral from 2 to infinity of 1 over x. Same idea. We're looking at I should have labeled this one here. So we're looking at the curve 1 over x. And they look essentially the same when I draw them because they don't look all that different. And we're starting at 2, going to b. Say, great, this integral is going to be the limit as b approaches infinity of the integral from 2 to b of 1 over x dx. We integrate. Limit's still there. So the limit is b goes to infinity. The integral of 1 over x is the natural log of the absolute value of x, evaluated from 2 to b. We plug in our limits of integration. You get the natural log of b minus the natural log of 2. You don't need to write the absolute values anymore because b is positive and 2 is positive. So we can kind of just write natural log of b minus natural log of 2. It would also be fine to write the absolute values still. And then it's important to know that as b gets really, really large, the natural log of b also gets infinitely large. This is going to be infinity minus the natural log of 2, which is infinity. So this integral, right, the integral doesn't exist in that the area under the curve isn't some finite value, right? It's not getting close to one particular number. It is diverging. So we would say that this integral from 2 to infinity of 1 over x dx diverges. Now, in this particular case, since the area is getting larger and larger and larger, we could be more specific and say the integral diverges to infinity. But sometimes an integral will diverge and it doesn't diverge in any particular direction. Just like it's not known whether it's getting infinitely large or negative or something else. So often you'll just say it diverges instead of diverges to infinity or negative infinity. Questions so far? Where's my examples here? Where are my examples? Somewhere over here. Sure. Welcome, welcome. Talking about improper integrals and whether they diverge or converge. So let's look at some more examples. I think he started you one like this in class. Oh, he did do one. Also, I was looking at your discussion sheet 4. There's some challenging integrals on there. Maybe we'll talk about some of them. What do you guys do with the discussion sheet? Do you do them in discussion? Kind of. Sure. Okay. Fair enough. What's that? Yeah. Well, no, there's a lot of questions on there. Let's look at this next one. The integral from negative infinity to 1 of 6 divided by 1 plus x squared dx. First things first, what's making this improper? The negative infinity, right? Any sort of infinity or negative infinity is always a sign that you have an improper integral. So the first thing we need to deal with is rewriting this with a limit. The limit as, you don't have to, but typically if it's a lower limit of integration, we use a. Some people use t or z, whatever. Like I'm going to use a. Limit is a approaches negative infinity of the integral from a to 1 of 6 over 1 plus x squared. And I should have done myself one more favor, but I didn't. I should have put the 6 out in front of the integral. But I didn't, so we'll live. So then that's going to equal, we have to write the limit every time. Okay, we're going to integrate 6 over 1 plus x squared. The 6 is hanging out. And the integral of 1 over 1 plus x squared is everyone's favorite, good old arctangent or inverse tangent of x from a to 1. Now here's where things get a little bit interesting. So when we plug it, we're just going to plug in limits. In fact, I feel like kind of you can skip this step and just go straight to like plugging your limits, but it's also good. So the limit is a approaches infinity, negative infinity. I should be careful with my language here, right? There's a limit that we're going to take eventually, but before that, we're plugging in the limits of integration. So first we're plugging in 1 and a. So we're going to get 6 times arctangent of 1 minus 6 times arctangent of a. What's the arctangent of 1? Yes, right. It's the angle. If you took tangent of it, you would get 1. So we're going to get 6 times pi over 4 minus 6 times what? Okay, well, as a goes to negative infinity, what happens to the arctangent of a? I think you mentioned this in class yesterday, but just to recap, here's what's happening. Here's what the arctangent graph looks like. It looks like you took the tangent graph, right, usual thing, and you reflected it across the line y equals x. So usually tangent has vertical asymptotes at negative pi over 2 and pi over 2. And we're just looking at the middle part of tangent. We're not looking at all the other ones. And then we're going to take that, and those vertical asymptotes are going to become horizontal asymptotes. So we have horizontal asymptotes at pi over 2 and negative pi over 2. And then arctangent looks like this. So instead of getting the point pi over 4 comma 1 like you would in the tangent graph, if you plug in 1, you get out pi over 4. And so you can see that as your input gets super duper negative, the output approaches negative pi over 2. So the limit as a goes to negative infinity of the arctangent of A is going to be negative pi over 2. It's a tricky one that people often have to be reminded about. Right? Because we don't often remember, yeah, pi over 2 for tangent. What we're really kind of saying here, think about it this way. If you took, I just want to point out, right? Here's your usual tangent graph. Or I should say, here's one period of the usual tangent graph with the vertical aspect of pi over 2, negative pi over 2, like this. So I will point out that as you take tangent of angles that are closer and closer and closer and closer to pi over 2, the output values get larger and larger and larger and larger and larger. So if you interchange the input and output with the inverse function, then for the arctangent function, as the inputs get larger and larger and larger, the outputs get closer and closer and closer to pi over 2. And I know I was talking about positive ones there, but really we ridiculous. So same thing is true for the negative pi over 2 part. So here we're going to get 6 pi over 4, which is, just factor out the 6, James. 6 times pi over 4 plus pi over 2, which is 2 pi over 4. So we're getting 3 pi over 4 times 6, so 18 pi over 4, or 9 pi over 2. But yeah, that probably will come up, that the limit as something goes to infinity of arctangent of that something is going to be pi over 2, or negative pi over 2 if you're going to negative infinity. I feel like this is a good time to look at one of these discussion questions. I feel like there's something on here that indicates he might expect you to know something that you might not know. I know you'd be shocked to hear that. So let's look at, this is 1D from the discussion sheet, just because I want to point out, yeah, the integral, yeah, sure, fine. It's similar, but a little bit different. From negative infinity to root 3 of 1 over x squared plus 9. And I would say the first step is still going to be the same. As with any improper integral, the first step should always be to rewrite it as a limit. Sometimes there's another first step before that, but assuming we just have a problem point or a problem infinity, we're just going to rewrite this as the limit. A approaches negative infinity of the integral from a to root 3 of 1 over x squared plus 9. So here's a good question. What's the integral of 1 over x squared plus 9? Well, it is an arctangent of something. So I would encourage you to memorize this because working out is kind of a pain. But let's go down here for a second. Let me show you the workout, and then we'll back up and we'll talk about what you need to memorize. So if you're integrating the integral of 1 over x squared plus, I'm going to write 9 as 3 squared. And we'll just do the indefinite integral down here. So really, you would love for this to be 1 plus something squared, or something squared plus 1. So what we're going to do is we're going to factor out the 9 from the bottom. So I'm going to rewrite this as 1 over 3 squared. I know I could write 1 over 9, but it makes more sense to write it this way. Integral of 1 over x over 3 squared plus 3 squared over 3 squared is 1. Notably, if I distributed this 3 squared back to the denominator, I would get right back here where I started. And now what you technically do is a u substitution. You let u equal x divided by 3, or 1/3 times x, the stuff inside the thing being squared right there. And then your du is going to be 1/3 times dx, so that 3 times du is going to be equal to dx. So then this integral ends up becoming 1 over 3 squared times the integral of 3 du over at the end here. And then we have a u squared plus 1. That could be a little brighter. The 3 and the 1/3 squared cancel one of the 3's to end up with a 1/3 not squared. And the integral of 1/u squared plus 1 is the arc tangent of u. Plus c, I guess, to be appropriate. And then we're plugging back in that u is equal to 1/3 x. We have 1/3 arc tangent of x/3. So here's the formula I do recommend you memorize if this comes up. If you keep seeing problems like this. So in general, if you are integrating something like 1/x² plus some number squared, like 3 squared or 4 squared or 5 squared or the square root of 6 squared, right? You could have 1/x² plus 6 and this formula would still be applicable. It's going to be 1/a times the arc tangent of x divided by a. Let's see. So fun fact, there you go. So then we can deal with this. So we're going to do this is going to be the limit as a approaches negative infinity of 1/3 the arc tangent of x divided by a, evaluated from, not a, x divided by 3. Sorry, I was going back to my formula there. Apologies. X divided by 3 from a to √3. And then we plug in our limits of integration. We get the limit as a approaches negative infinity of 1/3 arc tangent of √3/3 minus 1/3 arc tangent of a divided by 3. All right, let's do the fun part first. As a goes to negative infinity, a divided by 3 still goes to negative infinity, and the arc tangent of something going to negative infinity is still going to go to negative pi/2. So the second part is going to be minus 1/3 times negative pi/2. This first part here is going to be 1/3 times, what's the arc tangent of √3/3? It's not pi/4. You know that because arc tangent of 1 is pi/4. So let me ask you a question. Should it be an angle that's less than pi/4 with a bigger x and a smaller y, or an angle that's bigger than pi/4 with a bigger y and a smaller x? So tangent is y/x. So since my y thing is smaller than my x thing, I want the smaller angle with the smaller y and the bigger x. And the smaller angle we know that isn't 45 degrees or 0 is going to be 30 degrees or pi/6. That's one way to suss it out. And then we can simplify this. So we get pi/18 plus pi/6, something. Pi/6 is 3 pi/18 equals 4 pi/18 or 2 pi/9. Cool. So just be aware that that is something that you might see sometime somewhere. More. Oh yeah, let's do this one. Okay. Sometimes you're unlucky and you have both limits of integration being a problem, like the integral from negative infinity to infinity of 4x cubed e to the negative x to the 4th. And so here's the thing, you cannot write this with a limit right off the bat. And my kind of general thought here is that you can only deal with one problem at a time with improper integrals. This integral has two problems, as an infinity and negative infinity. So to be able to deal with each one of them separately, we have to break this integral up into two integrals. We can split it up wherever we like. A typical choice is at 0. But really, you can break it up wherever you want. You go negative infinity to 1 plus the integral from 1 to infinity, or 5 or 7 or whatever you like. But usually 0 is the choice people make. So we're going to have this as the integral from negative infinity to 0 of 4x cubed e to the negative x to the 4th dx plus the integral from 0 to infinity of 4x cubed e to the negative x to the 4th dx. And then we're going to rewrite this as the limit as a approaches negative infinity of the integral from a to 0 of 4x cubed e to the negative x to the fourth dx plus the limit as b approaches infinity of the integral from 0 to b of 4x cubed e to the negative x to the fourth dx. And then you kind of deal with each of them on their own. So you deal with them one at a time. And it's important to know, if both integrals converge, then the whole thing converges to whatever they add up to. If one of them diverges, the whole thing diverges. I should say, let me rephrase that. If at least one of them diverges, the whole thing diverges. And if you're not being asked about in what way the integral is divergent, then you don't really have to look at the second one. So usually when I'm doing a problem like this, if I can look at one of those things and be confident, or at least think one of them might be divergent versus the other one, I'm going to try and do the one that I think might diverge first. I don't think that's the case here. I think both of these are going to be convergent, because whether your thing is going to positive or negative infinity to the fourth is a positive infinity, and then the negative infinity, e to a negative infinity, is going to get real small. I think that e to the negative infinity, or 1 over e to the positive infinity, is going to overpower the 4x cubed. I'm pretty sure both of these are going to converge. Well, let's do the integration. So let's look at this one first. In fact, let's just do the integral off to the side. So the integral of 4x cubed e to the negative x to the fourth. What should I do? What method of integration am I looking at here? And what's my choice for you? Yeah, I would either say x to the fourth or even negative x to the fourth. I'd probably pick negative x to the fourth if I had a choice, but x to the fourth would also work out just fine. So then my du is going to be negative 4x cubed dx. I almost exactly have that, so I'm going to say that negative du is equal to positive 4x cubed dx, and then I'm good to go. My integral becomes the integral, 4x cubed dx is going to be my negative du, and then e to the negative x to the fourth is just e to the u. Since it being negative e to the u, I don't really care about the plus c here, because just for my own benefit, and that's going to be negative e to the x to the negative x to the fourth. And if you checked your work by differentiating, you'd be like, oh yeah, the derivative of that's definitely going to be negative e to the negative x to the fourth times negative 4x cubed, which will exactly be. The reason we're doing this over here is so that we don't like do it twice up here. Like I'm not trying to write the same work a bunch of times. So looking at just this part, that part's going to be equal to the limit as a goes to negative infinity of my integral, which is negative e to the negative x to the fourth, evaluated from a to 0. That part's going to be the limit as a goes to negative infinity of negative e to the 0 minus negative, so plus e to the negative a to the fourth. Personal opinion, I don't love an e to the negative infinity. I know it's 0, but I think it's nicer to write it as 1 over e to a positive. So I would prefer to rewrite this as the limit as a goes to negative infinity of negative 1 plus, instead of e to the negative a to the fourth, 1 over e to the a to the fourth. Because then I can say to myself, oh yeah, a is going to negative infinity. Negative infinity to the fourth power is positive infinity. E to the infinity is super big. 1 over e to the infinity is super small. So that's going to go away to 0. And then we end up with negative 1. Plus whatever this one ends up being. So then over here on this side, that's going to be the limit as b goes to positive infinity of negative e to the negative x to the fourth, evaluated from 0 to b. We do the same dance. We plug in our b and our 0. We get negative e to the negative b to the fourth minus negative e to the 0th. So that's going to be, I can just take, no, I was going to rewrite it, the limit. You might be more comfortable being like, yeah, I'm going to get e to the negative infinity and that goes to 0. That's also totally fine. It's just not what I like. So I have negative 1 over e to the b to the fourth plus 1. So b to the fourth is going to infinity, e to the infinity is big, 1 over a big number is going to 0. So then the whole thing adds up to 0. So this integral converges, and it converges to 0. An interesting thing to note here is that this function's odd. If you graph this function, let me graph it for you nicely instead of like trying to do it by hand here. In a moment. I should just have Desmos open when they come to class. That'd be smart. If we graph y equal to, what is it, 4x cubed, and then times e to the negative x to the fourth, that's not what I wanted there. You can definitely see it's a very odd function, and the area under the right side is going to cancel out the area under the left or above the left side, whatever you want to call it. Interestingly, you have to be a little careful here. I will just point out. Go away. I don't know why. Sometimes it's just like, sure, I'll go away. And sometimes it's like, you have to, yeah, there we go. I'll point out this integral is not equal to 0. I know it feels like it should be, but check it out. If you break it up, and then we deal with one of these, let's deal with this one here. That's going to be the limit as b approaches infinity of the integral from 0 to b of x cubed dx. We integrate, so the limit as b goes to infinity of x to the fourth over 4 from 0 to b. We plug in b, we get the limit as b goes to infinity of b to the fourth over 4 minus 0. And then if you plug in infinity, infinity to the fourth power is infinity. So this diverges. Which feels disappointing because it feels like you should say, yeah, but the other area is just as much negative area as that is positive area, so they should cancel each other out. But the problem is negative infinity plus infinity is an indeterminate form, and you cannot just say it's 0, even though it feels like it should be. So not every improper integral with an odd function from negative infinity to infinity is going to converge to 0. If it does converge, it will converge to 0, but it could diverge. I will also point out, I did not say it diverges to infinity or to negative infinity because we do not know. This piece diverges to infinity, and if you did the work, you could see that this piece diverges to negative infinity. So the only thing we can say for this entire integral is that it diverges, end of story. Yeah, let's look at a couple more and then we'll move on. So far all these have been what are sometimes called type 1 improper integrals, meaning your integral has either infinity or negative infinity or both in the limits of integration. Let's look at one or two more. That one, yeah, we should do that one. It's terrible. You're like, yay. Let's look at the integral from, we'll keep it nice. From 0 to infinity of x e to the negative x dx. Oh, let me turn off the little camera button thing there. Not a fan. All right, so first things first, we're writing it as a limit. Limit as b approaches infinity of the integral from 0 to b of x e to the negative x dx. And then to integrate this thing, how are we going to integrate x e to the negative x? Integration by parts. So here's the thing. I really, really don't like carrying all this machinery of the limit and the limits of integration when I'm doing a complicated integration process. So I highly recommend, and it's kind of true for any definite integral, whether it's improper or not. For definite integrals, if your integration technique is somewhat complicated, do an indefinite integral of that off to the side. So like over on the side here, you can be like, cool, the integral of x e to the negative x dx. Here's where I'm going to do my integration by parts. So I'm going to let u equal x. My dv is the rest, e to the negative x dx. My du is equal to the derivative of x, which is 1 times dx. And my v is the antiderivative of e to the negative x, which is negative e to the negative x. Toss it all into the ultraviolet super voodoo. We get u times v, so x times negative e to the negative x, minus the integral of v times du, so negative e to the negative x dx. Let's do a tiny bit of rewriting here. That's going to be negative x e to the negative x plus the integral of e to the negative x, which is going to be negative x e to the negative x minus e to the negative x. I mean, when you're doing the side work, you don't need to write the plus c. You can if you want to. I will point out, I'm going to be plugging in a positive infinity or a number that's getting big. As I've stated already, I don't like e to a negative big number. I would much rather rewrite this as negative x over e to the x minus 1 over e to the x. And actually, it's probably going to be most helpful if we do write this as one fraction. So I'm actually going to prefer to write this as negative x minus 1 over e to the x. You'll see why in a second. So now let's do the improper integral. So this is going to be the limit as b goes to infinity. We just found the antiderivative. It's negative x minus 1 over e to the x from 0 to b. We plug in the limits of integration. We get the limit as b goes to infinity of negative b minus 1 over e to the b minus negative 0 minus 1 over e to the 0. All right, here's a fun question. As b approaches infinity, what happens to the numerator of this fraction? Where's it going to? The numerator of this fraction? Negative infinity. How about the denominator of this fraction? Infinity. So we have an infinity over infinity type. Now, sometimes people are just like, yeah, but clearly the denominator is getting bigger much faster. Right? E to the b outpaces the linear function b minus 1 or negative b minus 1 leaps and bounds. But for some people, that's not good enough. Right? You're like, yeah, okay, cool, I agree, but also can you show your work, please? So here's the work we need to show. We have an infinity over infinity type, meaning, what rule do we have to use? L'Hopital's rule. So L'Hopital's rule, we're going to leave this part alone, but for this part over here, the limit as b goes to infinity, the derivative of negative b minus 1 is negative 1. The derivative of e to the b is e to the b. This part here is just minus 1 over 1, so that's a plus 1. We're just leaving that alone. Be light. And now we can actually take the limit, because as b goes to infinity, negative 1 over e to the b is going to get super small. So we're not surprised by this, right? We already kind of thought, oh yeah, the bottom is going to get way bigger, so the fraction is going to get super small. But it's good to be able to show our work using L'Hopital's rule. And it happens, I won't say a lot, but not never. I will point out that if we had written this instead as like negative b over e to the b and a minus 1 over e to the b, well, then you could be like, well, yeah, that one's going to go to 0 because obviously, and then that one you would have to use L'Hopital's rule on. I think it's more convenient just to combine them in one fraction and use L'Hopital's rule on that, but you could pick. It would be worse if it was x squared e to the negative x. Then you have 3 pieces, you don't have L'Hopital's rule. So again, combining those to make it less terrible. Good idea. All right. So those are limits. Those are integrals that are improper with either infinity or negative infinity or both as a limit of integration. But There's a whole other class of improper integrals that most of the 17B classes do not cover. Lucky you. Tadell typically does cover them. Which he did. He did in class, right? He did at least one or two examples where it wasn't that the integral had an infinity or a negative infinity, but the function you were integrating was undefined somewhere on the interval of integration. If you're lucky, it'll be one of the endpoints. If you're not lucky, it won't be. Here's what I mean. This problem, the integral from, let's make it fun, sure, 0 to 4 of 1 over the square root of, be smart about this, James, 4 minus x dx is not too terrible. I will point out that we'll see. Well, we'll do. I'm just gonna write this one for later on. We'll get there eventually. On the other hand, if someone gave you this integral, the integral from, say, let's be smart about this, James. The cube root, sorry, the integral from 0 to 9 of 1 over the cube root of x minus 8 dx. This one's less terrible because where is this function undefined? At 4, which is one of our endpoint limits of integration, right? It's only defined when x is less than 4, but not when x is equal to 4 or bigger than 4. But okay, we're not worried about that because on the other hand, here, this function is undefined where? Not 0. It's totally defined at 0. So actually, I want to pause for a second. 0 is totally okay here. 0 minus 8 is negative 8, but the cube root of a negative number is totally okay. Cube root of negative 8 is negative 2. But what's the problem point here? 8's a problem, right? Because 8's going to make you divide by 0. So this one, before you can start doing the improper integral stuff, you have to break this up into two integrals where 8 is the breakpoint. So you have to be able to deal with the problems, but the problems have to be one of your limits of integration. We'll come back to that. Here, 4 is the problem. So we're going to rewrite this as limit as b approaches 4 of the integral from 0 to b. I'm going to rewrite this as well as 4 minus x to the negative 1/2. And I've left off a small detail which is important.
I don't know if that's what you were about to say, but don't we have that like a plus or minus?
Right. So if we are between 0 and 4, are we less than 4 or bigger than 4? We're definitely less than 4, which means we're approaching 4 from which side? The left-hand side. So we're approaching 4 from the left. Typically, the way it boils down is if it's the upper limit of integration, you're approaching it from the left side because you're less than it. If it's the lower limit of integration, you're approaching it from the right side because we're bigger than. Okay, so now we do the work. So we're going to integrate this. We still have the limit out in front. Its limit is b approaches 4 from the left. Integrating 4 minus x to the negative 1/2, we get 4 minus x to the positive 1/2 divided by 1/2, which is the same as multiplying by 2. And then there's one other little thing I need to take care of. There's a minus sign in front of that x. It means the derivative would make me multiply by negative 1, so my antiderivative have to divide by negative 1, which is the same as multiplying by negative 1, so we're just going to put a negative sign over here. We could have taken more time and done a u sub. I don't think we needed to. Right? You could have let u equal 4 minus x. The problem with u sub, so I will say, for improper integrals, I do not recommend changing your limits of integration. Unlike u substitution problems where we're definite integrals, usually I'm a big fan of like, yes, you should change limits of integration, that's the way to go. Not the case for improper integrals. If we had done this with the u sub, I will just point out, if I had been like, yeah, I have the integral from 0 to b of 4 minus x to the negative 1/2, and I decided to do u equal to 4 minus x, and du is negative x dx, and so negative 1, James, not negative x. Crazy person. So negative du is equal to dx. So I rewrote this. I would write this as the integral of u to the negative 1/2 with a negative du. And I do not want to change these limits of integration, even though you could, right? You could be like, okay, yeah, if x is 0, u is 4. And if x is b, then u is 4 minus b. I don't like it. I don't recommend it. I don't think it doesn't make it easier, really. So I would just say, yeah, this is still from x equals 0 to x equals b. And then I would integrate and get negative u to the positive 1/2 divided by 1/2, which is multiplied by 2, from x equals 0 to x equals b. And then I would go back and say, oh yeah, that's negative 2 times 4 minus x to the 1/2 from 0 to b. So I do not recommend changing the limits of integration for improper intervals. It's just bad. It's one more thing to not have to think about, really, is what it's fun. Anyway, back to this. I forgot my limits of integration, 0 and b. Then we're going to plug in, the limit as b approaches 4 from the left of negative 2 times, I like to write this as a square root now, the square root of 4 minus b minus negative 2 times the square root of 4 minus 0. It actually is important that we're approaching 4 from the left-hand side. I will point out, if you took the limit as b approaches 4 from the right, that limit would not exist. Because even though you can plug in 4 and get 4 minus 4 is 0, if b is bigger than 4, this function is undefined. So it is important that we're approaching 4 from the correct side. And then we do just plug in, then we get negative 2 times the square root of 0 plus 2 times the square root of 4, which ends up being 0 plus 4, which is 4. Most of these types of improper integrals where your function is undefined somewhere on the interval of integration, most of them are undefined because you have division by 0 somewhere. And so what usually ends up happening is if your integral ends up getting the thing that was making you divide by 0 out of the denominator, usually it's going to converge. On the other hand, we'll see in this next example I'm going to do, if the thing that was making it undefined still is kind of in the denominator, then you're still going to be divided by 0 and it's still going to diverge. Let's look at the second example here. Not the one that's hiding behind here. We'll save that one for later. Maybe. Kind of a pain in the ass. We'll see. Okay, so let's look at another example where similar things are happening, but not quite the same. So let's do, sure, the integral from 1 to 6 of 1 of 7 divided by x minus 6 cubed. Clearly 6 is the problem, so we're going to rewrite this. We're going to write this as the limit. I should have made it the lower limit. Oh well. I'll make the next one the lower limit. Limit as b approaches 6 from the left-hand side of the integral from 1 to b. Be careful that your b's and your 6's don't look too similar. For me, that's a problem. And again, I think it makes sense to write this in a way that makes it easier to integrate. Let's write this as 7 times x minus 6 to the negative third power. Now, if we integrate this, the limit as b approaches 6 from the left, and then anti-differentiating 7 times x minus 6 to the negative third is going to give us 7 times x minus 6 to the negative second divided by negative 2. We don't have to divide or multiply by anything else special because our u sub would have just been u equal to x minus 6. Your d would have just been equal to dx, so it's not going to, there's not like a constant we need to worry about here. Evaluated from 1 to b. Now here's where it's easy to fool yourself. If I plot, in fact, let me write it out the kind of what I would say is not wrong, but not helpful. If I write this in the following way, the limit is b approaches 6 from the left, and let's be super careful that my b's and my 6's look different. Here I'm going to have 7 times b minus 6 to the negative second over negative 2 minus 7 times 1 minus 6 to the negative second. And if you're not careful, you might be like, okay, well, if I plug in 6, 6 minus 6 is 0, and 0 to some power is 0, and then you get 0 minus whatever that is. That's wrong. 0 to some power isn't always just 0. 0 to a negative power is undefined. So I'll point out here, note, 0 to the negative second power is the same as 1 divided by 0 squared, which is undefined. So that's why I don't like to leave my negative powers as negative powers. I would personally prefer to rewrite this as the limit as b approaches 6 from the left of -7/2 times 1 over b minus 6 squared plus 7/2 times 1 minus 6 to the negative. I should have rewritten that one too. Sorry. This one wasn't important, so I didn't rewrite it. Apologies. But then if you plug in 6, oh yeah, 6 minus 6 is 0, and division by 0 does not exist. We can be more specific here because we can see what kind of infinity we're going to have. If you plug in 6 from the left, slightly smaller than 6, so it's slightly negative, but you're squaring it, so it's positive. So this is like a positive infinity times a negative number. This is going to be a negative infinity plus 7 over 2 times 25, which nobody cares about that. That's negative. So this integral diverges, and if you care to state it, it diverges to negative infinity. Graphically, here's what's happening. You graph this thing. Let me show you something cool, actually. So if you graph this, 7 over x minus 6 cubed. So you can kind of see what's going on here. And actually, if you want to look at the area under the curve, or above the curve, I guess in this case, because right, it's below the x-axis, you can actually do something kind of neat. You can say, I really want y to be bigger than that. And then less than or equal to 0. And then you can even change, you can say that x should be between 1 and, sorry, not, yeah, 1 and 6. So there's the whole area that we were just kind of trying to find. Oh yeah, it's definitely negatively infinitely large because it's all below the x-axis. Kind of neat. I mean, if you, scrolling down there is not going to show you anything that you can't already see. So that's kind of the idea there. That's why this integral is diverging to negative infinity instead of positive infinity. Again, not super duper important to say which way it diverges. We could have just said diverges, and that should have been enough. Yeah. Occasionally, if you're doing web work, sometimes it might ask you which way it diverges, but you guys aren't doing web work, so not an issue. Yeah, well, we'll do that. So one thing you have to be careful about is, I think there's a problem kind of like this in class. Let's do, yeah, I'm gonna do something slightly different. Something like this, the integral from negative, let me think for a second here. Sorry, I want this to turn out in a way that's obvious. Sorry, I have to think for a second. Let's go from -2 to 1. Is that gonna be right? I think it's gonna be right. Sorry, 1 over x squared. Hopefully it comes out right. We'll see. So if you weren't being careful, it'd be really easy to get this wrong. You're like, oh yeah, cool, I can integrate that. That's going to be -1 over x from -2 to 1, which is going to be, oh, darn, I think it's going to come out. Oh, it's going to go fine. -1 over 1 minus -1 over -2, which is equal to -1 minus 1/2, right? Which is equal to -3/2. Cool, let me graph it for you. 1 over x squared looks like this. And what we just said is the area under this curve, it's always above the x-axis, from -2 to +1, we just said all that area was -3/2. Does that seem at all reasonable to you? Definitely not. And the problem here is that that function is undefined somewhere on the interval of integration. So to actually appropriately do this, we have to break it up at the place where it's undefined. So this integral, right? So let's be super clear. That is not correct. So when you have a definite integral, and again, there've been a couple he's done in class earlier in the quarter that technically were improper, and he just wasn't kind of paying attention. But from this point on, unless someone says like, you know, it's definite and defined, or if they don't say, you should be like, ooh, is that function undefined somewhere? Let me double check real quick. So this function is clearly undefined at 0. We have to break it up at 0. So we're going to write this as the integral from -2 to 0 of 1 over x squared dx plus the integral from 0 to 1 of 1 over x squared dx. And let's just deal with one of these pieces because I'm pretty sure it's going to diverge, but let's check it out. So if we look at this piece here, we're going to rewrite that as the limit as a approaches 0 from the right of the integral from a to 1 of 1 over x squared dx. If you look at that, it's going to be the limit as a approaches 0 from the right. The integral of 1 over x squared, again, is negative 1 over x, evaluated from a to 1. So we get the limit as a approaches 0 from the right of negative 1 over 1 minus negative 1 over a. And as a goes to 0, 1 over a is going to blow up to infinity. So we get minus minus, so we get plus infinity. So it's going to be infinity. So it diverges. And we don't even need to look at the other half, right? Once one piece diverges, it doesn't matter what the other one is doing. It only matters a little bit if someone asks you, does it diverge to infinity or negative infinity, or we don't know. Because in this case, the other piece would also diverge to infinity, and then infinity plus infinity is infinity. So technically this whole integral diverges to infinity. But again, I'm just trying to say all the things, but usually people aren't asking about that. So I would try not to worry about it too much. I'm just saying it because I can't not say it. What else? There's something else I want to say about this. No, I think that's it. Let's look at this discussion sheet for one more second here, which is somewhere in my pile of papers. There we go. Want to see if there's any others that look kind of super heinous on here. Oh, that's kind of terrible. Sure. Yep. Okay, fine. We'll do one like that. Sorry, I'm just looking here and seeing. Yeah, these are wow. Oh, and that too. I wonder how much he looks at these discussions. I feel like because you guys definitely didn't talk about the comparison test, right? Right. Yeah, good question. What is the comparison test? The comparison test says, so here's the gist. So here's the comparison test. I don't know if you need to know this, but it's pretty easy to figure out. So we'll say the comparison test. And this is usually only true for positive functions. So if you have a function f of x that's always positive, and f of x is always less than or equal to another function g of x on some interval. It might be from a to infinity, it might be from a to b, whatever. So what we're really saying, we're saying that g of x is bigger than f of x, and f of x is smaller than g of x. So there's two things we can say here. Thing one, if the integral on whatever interval from, say, a to b of g of x, where b could be infinity, if this integral converges to some finite value, then that means that the integral of f of x also has to converge because there's less area that f of x has. So if the bigger function integral is convergent, then the one smaller than it is also convergent. And then kind of the opposite thing is also true. So if the bigger one converges, then the smaller one is stuck having to converge. If the smaller one diverges, if the area under the smaller function is infinitely large, essentially, then the function that's bigger than it also has to have an infinite amount of area. So the second thing is that if the smaller function's integral, so if the integral from a to b of f of x diverges, then so does the other one. And the integral from a to b of the larger function also diverges. That's what the comparison test says. So looking at what he's got here, for example, sure, let's look at that one. That one, sure, that one. That's another one. So here's one of the examples he has. The integral from 1 to infinity of e to the negative x squared dx. And if I haven't said it already, e to the negative x squared, famously not antidifferentiable. Kind of the most famous function that does not have a nice antiderivative. So our job here is to figure out if we want to try, if we think it might converge or diverge. Well, I'll point out e to the negative x squared is 1 over e to the x squared. And if I made the exponent smaller, I would make the fraction denominator smaller. I'd make the whole thing bigger. So I'm pretty confident that this is less than 1 over e to the x. Right? Because x squared is bigger than x, at least if x is bigger than 1, which it is, right? Our interval is from 1 to infinity. So x squared is bigger, I guess it's bigger than or equal to x on the interval from 1 to infinity. So that means e to the x squared is bigger than or equal to e to the x. And then when you take the reciprocal of both sides of an inequality, it changes the direction of the inequality. 2 is smaller than 3. 1/2 is bigger than 1/3. So when you take the reciprocal of both sides of an inequality, it changes the direction of the inequality. If you don't like that, just do cross division instead of cross multiplication, so you could also, instead of doing that, you could divide both sides by e to the x. And you can divide both sides by e to the x squared. Oh, look, it's the same inequality. That 1 over e to the x is bigger than or equal to 1 over e to the x squared. But the faster way of just reciprocal. So great. Here's what that means for us. It means that if the integral from 1 to infinity of 1 over e to the x converges, then this also converges. And it does, because this integral is the limit as b goes to infinity of the integral from 1 to b. I'm going to write this as e to the negative x. I'm going to integrate. If the limit as b goes to infinity, integral of e to the negative x is negative e to the negative x from 1 to b. Rewrite it as the limit as b goes to infinity. I'm going to write it as, instead of negative e to the negative b, I'm going to write it as negative 1 over e to the positive b and minus negative 1 over e to the first. And then as b goes to infinity, 1 over e to the b goes to 0. So I end up getting 0 minus, so plus 1 over e, which is 1 over e, which converges. So since this integral is convergent, and this integral's function is smaller than that integral's function, this integral also converges. So that means that the integral from 1 to infinity of e to the negative x squared dx converges by comparison. Something I want to say there. The hardest part about using the comparison test isn't showing that the integral you're comparing to is either convergent or divergent typically. It's figuring out what to compare it to. That is the hard part. Yeah.
Do you ever have to prove that the function you're comparing to is less than or greater than?
No, usually people are gonna just buy, like, as long as you're correct, it's no one's gonna be like, yeah, you have to show it. No, not typically. It's usually also not too terrible to do that. Let's look at one more example from this handout because I think we should try to show the opposite way. So let's also look at 4b. That was 4a. I'll just point out from this discussion sheet. 4b is the integral from 1 to infinity of 5 over the square root of x plus the square root of x. And here's what I would point out. Usually other stuff inside the square root is kind of a red herring. Like it's kind of misleading us. I would just ignore that root x there. And so I would just think about for a second, well, cool. Does the integral from 1 to infinity, I don't really care about the 5 either. The 5 is kind of whatever. I guess I'll write it. Let's just think about what's going to happen. If we did this integral, if we integrated 1 over the square root of x, we would end up getting x to the positive 1/2. right? Because that's really x to the negative 1/2. The integral is x to the positive 1/2. We don't care about the coefficients. So this integral is going to be something like the square root of x evaluated from 1 to infinity. I know this is bad notation here. I didn't write a limit or anything. I ignored the 5. I ignored the 1. What doesn't matter. I'm just trying to see, do I think this integral is going to diverge or converge? In this case, the square root of infinity is divergent. So we're pretty confident we think this is going to diverge. It does. But we're not going to finish it off until we go over it. So what that means is if this is divergent, which I think means this isn't going to work out very well. I think I'm not going to compare it to this because the problem is I need that this whole thing needs to be bigger than that thing if it's going to be divergent. And the problem is I think 5 over the square root of x plus root x. Well, if you make the denominator bigger, you make the fraction smaller, which means this fraction is smaller than that fraction, and that's not what I wanted. Bummer. Yeah. So how do we fix it? Good question. I don't know the answer. Yeah, I don't know. Yeah. Right? Yeah, that's wrong. I want something. So what I want, because I'm of the mind that I'm pretty confident this is going to diverge. It's kind of like that. So what yeah, okay, there's that. I really want 5 over the square root of x plus the square root of x to be bigger than something that I think is going to diverge. Well, ugh. So this is coming back to your question, Giancarlo. Sometimes you might have to actually kind of show that it is either bigger than less than. So an easy way I could make this thing smaller is to lose the 5. So is this bigger than 1 over root x? Okay, here's the not fun part. I'm going to try to figure this out. So I'm going to cross multiply. Square both sides. Both sides are positive. Squaring both sides won't change the direction of the inequality. Kind of funky though. I'm going to subtract x from both sides. I'm going to square both sides again. 24 squared is 476. Yeah. 476. Is 476 x squared bigger than x? Yes, certainly if x is positive, bigger than 1. So yeah, that checks out. Cool, that was super annoying. But it does check out. So cool, that means that's bigger than that. And then we can say, great, now our job is just to show the integral from 1 to infinity of 1 over root x diverges, which you can all do on your own. And that will show that the original integral from 1 to infinity of 5 over root x plus root x dx diverges by comparison. So as I said earlier, sometimes it's really challenging to figure out what to compare it to get what you need to happen. Yeah. And I wish I had better words to say about that, but that's kind of the story. That's the story. All right, so in the last 15 minutes here, let's move on to talking about area between curves. That's what's coming up next. So yeah, some examples. Okay. So let's look at something. I want to find the area between y equal to x squared minus 2x and y equal to 3x. And I'll say blanket statement. Generally, we prefer not to have to graph these. It's still a good idea to graph it to kind of see what's happening, but we'll eventually try to show how we do this without graphing. But in this case, we are going to graph. So I'm gonna graph both these functions. One of them is a straight line that goes to the origin. So let's do some colors. I got colors. So here's my y equals 3x, not drawn very accurately because I want my graph to be easy to see. So here's my y equals 3x, although it looks more like I drew y equals x. Oh well. And then x squared minus 2x is an upward opening parabola. If you factor it, you can see you're going to have x-intercepts at positive 2 and 0. The parabola looks something like this. We're trying to find the area between these two graphs. So here's the area we're trying to find. It's a shaded region here. And what you really want to think about is kind of just like before when we were finding area under a curve, we're adding up the areas of a bunch of really skinny rectangles. So we're going to draw a representative rectangle somewhere in the middle. There's my rectangle there. And I'll point out that the area of our little rectangle is just going to be base times height. The base is a small change in x, which we're going to call dx, or delta x if you prefer back for dx. I know I'm going to move to an integral. And the height of this rectangle, well, it's whatever value the top function has minus whatever value the bottom function has. We often just write top minus bottom to start off with. And then if you have the graph, it's really easy to see which one's on top, which one's on the bottom. So graphically, we can see that the y equals 3x function is higher up than the y equals x squared minus 2x function. So that's the area of our rectangle. And then to find the total area, we're going to add up all the rectangles or integrate. But to be able to do that, we have to know what the limits of integration are. So to be able to do that, we're going to find where these two graphs intersect each other. So to find the point of intersection, we're just going to set x squared minus 2x equal to 3x. Bring everything to one side. You get x squared minus 2x minus 3x is minus 5x, 0. Factor out an x. You're left with x times x minus 5 equal to 0. So either get x equal to 0, no surprise, or x equal to 5. And if x is 5, not that you need to know this for this one, but the y coordinate would be 15. That's your point of intersection there. So here's something kind of interesting. If we hadn't graphed it, we could have figured out which function was on top by picking a number between 0 and 5 and plugging it into both functions and seeing which function was bigger. So for example, we plugged in 1. We plug in 1 to the parabola, you're going to get 1 squared minus 2, which is negative 1. Plugging in 1 to the straight line, you're going to get 3 times 1, which is 3. And 3 is bigger than negative 1. So we can see that the straight line part is the bigger function, at least on the interval where we're finding the area between them. Right? It's clearly not always the bigger function, but it is between 0 and 5. So then to find the total area, we're going to, again, add up all the rectangle areas or integrate from 0 to 5, our top minus our bottom times dx. In this case, that's going to be the integral from 0 to 5 of 3x minus x squared minus 2x. Do be careful here, right? It's got to be minus the entirety of the lower function so that if there's more than one term, the minus sign has to distribute. So I would probably simplify before I integrated. I get 3x minus 2x is 5x minus x squared. Now we can integrate and get 5x squared over 2 minus x cubed over 3 from 0 to 5. We plug in 5 and we get 5 times 5 squared, which is 125 over 2, minus 5 cubed, which is also 125 over 3, minus 0 minus 0. And then to simplify this, I'll point out there's something really easy you can do. I don't love subtracting fractions with large numbers in them. So great, I'm going to factor out the 125. I could definitely write this as 125 times 1/2 minus 1/3. And then to me, that feels easier to manage. 1/2 is 3/6, 1/3 is 2/6, and 3/6 minus 2/6 is 1/6. So this ends up being 125 times 1/6, or 125 over 6. And that's how much area is between these two curves. Yeah, let's look at one more example here. Okay, so let's. I imagine he will go this way as well, so I don't feel like I'm saying anything inappropriate here. So let's find, yeah, we'll say find. So find, so I kind of just said something before that is true, something. So typically we don't want to have to graph them, but if you're finding the area between more than just two curves, like if you have more boundaries than just two curves where they intersect each other, you kind of have to graph it. So this next question we kind of have to graph. Find the area bounded by the curves f of x equal to x squared, g of x equal to 1 over x, and y equal to 9. So if you've got more than two things going on, you kind of need to draw it. So let's draw it here. Let's see. And so I know I'm not drawing all of these graphs because I know what this looks like. So yes, I know 1 over x has like stuff down over here. I'm not going to draw that because I don't need it. So here's my 1 over x. And then here's my y equals x squared, or my f of x equals x squared. And here is my y equal to 9. When you're finding the area bounded by some number of curves, it has to be the region that, yep. So I knew I was forgetting to say one thing. In quadrant 1. Because technically, right, if I extended this parabola further left, this y equals 9 would intersect the parabola. And you could be like, well, James, there's a region over here to the left that's bounded by both your red curve, your blue curve, and your black curve. But I don't want that one. I want this one here in quadrant 1. That's the region. Or let's label my one. So here's y equals 9. Here's f of x equal to x squared. Here's g of x equal to 1 over x. And this one's a little problematic. Because unlike the previous one, where I drew a vertical strip, is what I usually like to call that. Anywhere I drew this strip, the upper and lower boundaries are the same. The top is always y equals 3x. The bottom is always y equal to x squared minus 2x. Not true for this other problem. If I draw a vertical strip in this region, well, if I draw it over here, the top boundary is y equals 9. The bottom boundary is g of x equal to 1 over x. But if I draw it over here, the top boundary is y equals 9, but the bottom boundary is f of x equal to x squared. So the problem with this is to find the area bounded by these three curves, I have to break this up into multiple intervals. I have to break it up right here. So let's find where those two functions intersect each other. So I set f of x equal to g of x. So x squared equal to 1 over x. I bet you all could guess what number is the answer. What number squared is equal to 1 over that same number? 1, right? 1 squared is 1, 1 over 1 is 1. Yeah, you could do more work, like you can multiply both sides by x and then say x cubed equals 1 and take the cube root and get x equal to 1. But if you can guess the right answer, that is also okay. So cool. this first integral is going to be from something to one, and the second integral is going to be one from one to something. So, oh, I knew that was going to happen. So, hang on, you can do it. You can make it. Maybe. So, let's wrap it up here. So, finding this point of intersection, I'm going to set 9 equal to 1 over x. So, setting 9 equal to 1 over x, I'm going to get 1/9 equal to x. So, that's the point right there. 1/9, comma 9. This pen's kind of dying. And then similarly over here, saying x squared equal to 9. I think the answer is obvious. We're going to get x equal to, actually technically plus or minus 3, but since we're in quadrant 1, we want x equal to 3. The point there is 3, comma 9. So to find the area, well, this first area here, we're going to do the integral from 1/9 to 1 of the top 9 minus the bottom 1 over x. Plus, then for the second region here, we're going to do the integral from 1 to 3. The top is still 9. The bottom is x squared. And we won't compute this because I want to show you something else instead, which is that we could also do this a different way. So alternatively, darn it.